In this video, we discuss the concept of higher order derivatives. The derivative we've been discussing so far is also known as the first derivative. So for instance, if f of x equals x to the fifth, we can differentiate and we get that the first derivative f prime of x is 5x to the fourth. Well, we don't have to stop there. We can differentiate again. And the result is called the second derivative, and it's denoted by f double prime. It's hard to see here, but that's actually f with two prime marks, f double prime of x. And then we continue in a like fashion. The third derivative we would write as 60x squared. The fourth derivative would be 120x, but at this point we usually change notation a little bit. We modify it to make it more convenient. You can see that if we had to write a whole lot of prime marks, that would be inconvenient. The person who was reading what we were writing would have to count the primes, and so that's not any good at all. So usually about the fourth derivative, we do everyone a favor, and instead of writing, say, 4 prime marks, we just put 4 up there in parentheses. And so the fourth derivative would be 120x, and the fifth derivative would be 120, and then the sixth derivative would be 0, and all subsequent derivatives would also be 0, the seventh, the eighth, and so on. So let me say a little bit about notation. If you're using the Lagrange notation, the prime notation, well, we've already discussed what to do in the case of the f of x notation. You just put prime marks and then start counting them after a while. While you do the same thing with the Lagrange notation when you're using y. The Leibniz notation takes a little bit of care. The first derivative of y is denoted dy dx, as we've already mentioned. The second derivative is d squared y over dx squared, and then the order of the derivative is indicated by the superscript on the y in the numerator and the x in the denominator. Now, just to show where that comes from, if you're finding the second derivative, what you're doing is you're taking the first derivative and you're differentiating that with respect to x. So you take the first derivative and then you differentiate this with respect to x. And so mathematicians just write that as d squared y over dx squared. The dx being thought of as a single quantity. It's not d times x, it's just dx. And that is a more compact notation. Alright, so let's try an example or two. Here we've got y equals x cubed plus sine x. We're asked to find d squared y over dx squared. You need to know that that means the second derivative. So dy over dx would be 3x squared plus cosine x, and then d squared y over dx squared would be 6x minus sine x. Now let's try the example y equals secant x. I hope you remember the derivative of the secant function. it is secant x times tangent x. Now to find the second derivative, we need to differentiate the first derivative, but now this first derivative is a product, so we're going to need to use the product rule to find the derivative of secant x tangent x. But we've already done that. We know that the derivative of tangent x secant x, which is the same thing as secant x tangent x, is secant x times the quantity tangent squared x plus secant squared x. So I'm just going to write secant x times secant squared x plus tangent x, tangent squared x rather, and I'm going to say this is from previous work. All right, an application of higher order derivatives involves motion. We've already seen that if we have a position function, s of t, that its first derivative, v of t, gives us velocity. That's the rate of change in position with respect to time. Well, if we look at the second derivative, if we differentiate the velocity, what we're getting is the rate at which the velocity changes with respect to time, and that is called the acceleration. What is the acceleration of a falling body? Well, we know that the position function for a falling body is in, let's say, metric units, negative 4.9 t squared plus v naught t, v naught being the initial velocity, plus s naught, the initial position. So v would be, remember, let's see, that would be negative 9.8 t. We're treating the v naught as a constant, so we've got a constant times t. We're differentiating with respect to t. That derivative would be v naught, and then s naught is a constant. Its derivative is 0. So the acceleration, which we denote with by a of t, is going to be the derivative of v of t. So the derivative with respect to t of negative 9.8 t is just negative 9.8. And then the derivative of v naught is going to be 0. Now just a word about units. Since we're using the metric system, this equation gives the position in meters, the velocity in meters per second, and then the acceleration would be in terms of, well, units of velocity per second squared.